Greetings. This is section 4.9 on antiderivatives. We are studying from James Stewart's Early Transcendentals Calculus text, the 8th edition, and we are studying the applications of the derivative, and this section is on antiderivatives. So we are going to be doing differentiation in reverse. We're going to be finding functions whose derivative is equal to what we are given. So let's look at the definition of an antiderivative of a function f. Okay, so we're looking at this definition here. A function big F is called an antiderivative of little f on an interval I if the derivative big F of x is equal to little f of x on all x. Okay, so we're trying to find what function has derivative equal to the function that we are given. So let's do some practice here. If we're looking at little f of x equal to 1, what function has derivative equal to 1? Well, I can think of big F of x equal to x, right? What's the derivative of x? 1. But also, I can think of f of x equal to x plus 500, or I can think of f of x equal to x minus 7,000, or I can think of f of x equal to x plus pi, because we know pi is a constant also. So what would a general antiderivative of little f of x be? A general antiderivative would be x plus c, where c is any real number. It can be 0, it can be positive, it can be negative. Good. Looking at f of x equal to 2x, what function has derivative equal to 2x? Well, I can think of big F of x equal to x squared. What's the derivative of x squared? 2x. So x squared is going to be an antiderivative, but we want to remember that if f is equal to a constant, then f prime is going to equal 0, and anything plus 0 is itself. So I can think of other antiderivatives. A big F of x could be x squared plus 2. Another antiderivative could be x squared minus 7. Another antiderivative could be x squared minus e, because we know e is a constant as well. So what would our general antiderivative be? Our general antiderivative would be x squared plus c, where c is any real number. Right? Because take that derivative there, the derivative of x squared plus a constant would be 2x plus 0, and that's still going to be 2x. So we can build on that with our transcendental functions. What function has derivative equal to cosine x? I know that sine x, right? Because we know that the derivative of sine x is going to be cosine x. So we can think of other antiderivatives. We can have sine x plus pi. We could have sine x minus 500, etc., etc. So our general antiderivative is going to be sine x plus c, where c is equal to any real number, right? Because f prime of x is going to be cosine x plus 0, which is our cosine x. So our big F of x, our general antiderivative, is going to be the function whose derivative is the function we are given. Good. So let's take a look at this theorem here. We've got if f is an antiderivative of little f on an interval, then the most general antiderivative is going to be big F of x plus c, and we know that f prime of x is going to be little f of x. Okay. So in looking at the graphical representation of the most general antiderivative, we're going to be given a family of functions that are just separated by a vertical translation of c, where c is just an arbitrary constant that could be positive or negative, but we know that at any point x, the derivative, which is the slope of the tangent line at that point, is going to be the same for each value of x, right, with vertical translations. All right. So in the back of your textbook, and in general in the back of most calculus textbooks, you're going to find a basic table of antiderivatives, or a basic table of what they call integrals. And this is just a subset of that. But remember, what is an antiderivative? We're finding a function. The antiderivative is a function whose derivative is the function that you are given. We can use our algebra of derivatives. We know that a constant times a function, the derivative of that is going to be the constant times the derivative of that function. The derivative of a sum or difference is going to be the derivative or the difference or sum of those derivatives, right? And keeping in mind that the derivative of that antiderivative is going to be the function itself. So the derivative of big G of x is going to be little g of x. Okay. We can skip ahead before we have our most powerful power rule, pun intended, we can see that if we've got e to the x, what function has derivative equal to e to the x? E to the x does. What is the derivative of cosine? Sine, right? So the antiderivative of sine is going to be cosine. What function has derivative equal to sine x? Negative cosine x, right? Why? Because we can see that the derivative of minus cosine x is going to be minus sine x, which is going to be sine x. And we can see that that is equal to our antiderivative. Good. You don't see the plus c's here because they're looking at particular antiderivatives, right? This is just one. A particular antiderivative is just one antiderivative. A general antiderivative is going to contain the plus c. Good. And so they continue with a second set or a second column. What function has derivative equal to secant squared x? Tangent does, right? Because we know that the derivative of tangent x is equal to secant squared x. What function has derivative equal to secant tangent? Secant does, so we know that the derivative of secant x is secant x tangent x. So we're kind of going in reverse, okay? And very common in integral calculus, and we're moving towards integration. That's the next section of calculus that you will study in the next semester. That inverse sine is very common in integration, and inverse tangent is common in integration. So if we know that the derivative with respect to x of the inverse tangent of x is equal to 1 over 1 plus x squared, then the antiderivative of 1 over 1 plus x squared is going to be the inverse tangent of x. Good. And you have some sample hyperbolic cosine and hyperbolic sine. I encourage people to check out your lists or your basic table of integrals, which is your basic table of antiderivatives. So now I want to make or point out the very powerful power function. Remember that if we've got y equal to x to the n, then y prime, we would be taking the exponent down, and then we would be subtracting 1. So if we're going to undo that process, it's almost like going to your friend's house and then going home. You kind of reverse the steps that you took to get there. So what was the last thing I did to take the derivative? The last thing I did was subtract 1. So the first thing that I'm going to do then is to add back 1. And I'm going to introduce some antiderivative notation, which will make sense in the coming chapter when we study the fundamental theorem of calculus. The anti-notation is the integral. And so we want to say that the integral of your y prime is going to be y plus c, or the integral of your little f of x dx is going to be your big f of x plus c, your general antiderivative. Find the big function f of x whose derivative is equal to the little f of x, or find that big function y whose derivative is equal to y prime. So the last thing that we did, so if we're taking our integral of x to the n dx, and you find that integral sign in that basic table of integrals, and that is that basic table of antiderivatives. The very last thing that you did was subtract 1. So the very first thing you're going to do to undo the derivative is to add 1. And then what did you do before that? When you took the derivative, you took that exponent down, that bigger exponent down, and you multiplied. So what's the opposite of multiplication? Is going to be division. So, and what are we dividing by? That big exponent. So we're dividing by that n plus 1. But of course, for the general antiderivative, we don't want to forget to add the plus c. So you'll see that in here in this example. Okay. So let us practice with some general antiderivatives here. So here it says find the antiderivative of the given function, and let's do general antiderivatives. Well, just like with root x and taking derivatives, we usually transform that to an exponential notation so that we can use the power rule. So we can see that this is x to the 1/2. So if I'm going to use that integral notation, f of x dx, that's going to be the square root of x dx, and you're going to see the integral, we want to change that to x to the 1/2 dx. And we have x to a number, so we can use the power rule for anti-differentiation. So when I do that, this is going to equal x to the 1/2. I'm going to add 1, and then I'm going to divide by that entire denominator. And we're not going to forget to add plus c. What is 1/2 plus 1? 1/2 plus 1 is 1.5, and 1.5 is 3/2. What is division by a fraction? Division by a fraction is multiplication by the reciprocal. So we can rewrite divide by 3/2 as 2/3 times x to the 3/2 plus c. And that is going to be our answer. This next one might look a little complicated, but you're going to learn in the next semester of work techniques of integration or techniques of anti-differentiation, because it's going to have many different applications that are very useful in the real world. So our first technique of integration is just like the techniques of differentiation that we have. Sometimes we might need to algebraically manipulate the expression before we can get at basic techniques of differentiation. So I might want to rewrite this expression as t cubed over t squared plus 6t over t squared plus 4 over t squared. T cubed divided by t, that's just undoing our fraction addition. T cubed divided by t squared is just going to give me t. 6t divided by t squared is just going to give me 6 times 1 over t. And I might want to rewrite 4 over t squared as 4 to the t minus 2. And now if I wanted to take the antiderivative here of f of t dt, that is going to be, in your dt, your differential is going to become more apparent in the next chapter. So it's just a notation of find the antiderivative in this section. Is going to be, I'm going to just copy the t plus 6 times 1 over t plus 4 times t to the negative 2, and I'm taking that with respect to dt. Remember from above, just like the derivative of a sum is the sum of the derivatives, the antiderivative of a sum is the sum of the antiderivatives. So we can split these up as the integral of t dt plus, and the derivative or the antiderivative of a constant times a function is that constant times the antiderivative of that function. So this is going to be plus 6 times 1 over t dt. Same thing, we can put the 4 on the outside times minus 2 dt. We can look at the t as t to the first power, and I'm using my power rule in this instance, and this is going to be what if I have t, I'm integrating with respect to t, or I'm finding the antiderivative with respect to t, and t is my base to a number, I can use the power rule for that. So I can add 1 to my exponent and divide by that 1 plus 1. I have plus that constant. And what function has derivative equal to 1 over t? We want to say ln of the absolute value of t. And we just want to guarantee, because the domain of the ln of t is positive, we want to make sure that that value of t is positive, so we throw that into absolute value. We continue with 4, and we still have t to the negative 2. So we can say this is t to the negative 2. We're going to add 1 to that exponent and divide by that same exponent. And then finally, we don't want to forget to add plus c. So now we want to clean things up. And I'm going to get t to the 1 plus 1 is t squared. And 1 plus 1 is 2. I can still keep ln of the absolute value of t. We have negative 2 plus 1 is minus 1. And we still have minus 1 plus c. And now I can take care of that plus and that minus. And I can also take care of the t to the minus 1 and put that downstairs. And finally, we can say that our big f of t here is t squared divided by 2 plus 6 times the ln of the absolute value of t. And we're going to say minus, and we're going to have 4, and we can put the t downstairs to t to the first power plus c. And that should be our final answer. And how can we confirm that that is our final answer? You can check by saying, does f prime of t equal little f of t? And you can check that way. In our final example for this video, let's look at f of theta equal to secant squared theta minus secant theta tangent theta. And if I'm finding the general antiderivative, we are taking the integral of f of theta d theta, and that's going to be the integral of secant squared theta minus secant theta tangent theta d theta. Remember, the antiderivative of a difference is the difference of the antiderivatives. So this is going to equal the integral of secant squared theta d theta minus the integral of secant theta tangent theta d theta. We are taking derivatives in reverse. What function has derivative equal to secant squared theta? Tangent does. What function has derivative equal to secant theta tangent theta? Secant does. And we don't want to forget to add our general antiderivative notation. We're going to add an arbitrary constant. And that is going to be our answer here. And again, we can check if big F of theta, is equal to tangent theta minus secant theta plus c. What is f prime of theta? The derivative of tangent theta is secant squared theta. The derivative of secant theta is secant theta tangent theta. And the derivative of a constant is 0. And so we would get secant squared theta minus secant theta tangent theta, and that does give us our f of theta. Good. So please practice your antiderivatives. Remember, you are taking differentiation in reverse. We do have the main ideas here are the derivative of a constant times a function is the constant times the derivative of the function. So we can pull constants out of our integral signs or our antiderivative signs. We also have that the derivative of a sum or difference is the sum or difference of those derivatives. And so we can take them term by term. We have the ever powerful power rule. And so in taking antiderivatives in reverse, we are going to add 1. If we have x, if we're integrating with respect to x, so our variable x is in the base, we're going to add 1 to our exponent, and then we're going to divide by that entire exponent. And then we're not going to forget to add the plus c. Good. What function has derivative equal to 1 over x, ln of the absolute value of x? And so we have some various transcendental function, antiderivatives of transcendental functions. All right. The first couple examples here, as I mentioned, sometimes it might be necessary to algebraically manipulate your expression to get to a point where you can use the basic table of values. All right. So the next section, we're going to be looking at what's called the initial value problem. So instead of coming up with a general solution, we will be finding a particular solution that passes through a specific point. And that concludes this first video of section 4.9. Be on the lookout for a second one.